All right, so today we'll be talking about thermal energy storage, several varieties of thermal storage, and we'll talk about water heaters as kind of an interesting special case of thermal storage that comes up in residential and some commercial buildings. Hopefully we'll finish with a little bit of time remaining, and then I'll walk through a little bit of the homework that you guys have that's due next week. Okay, so we'll begin by talking about three types of thermal energy storage. One that's called lumped sensible, so temperature change. We talked about sensible versus latent heat last time. So we'll talk about storing energy basically via temperature change versus via phase change. And then within the sensible thermal storage, there's kind of two interesting types. And one is when you have sort of a lumped temperature distribution, so the temperature is pretty uniform throughout the storage medium. And another is when you have what's called a stratified temperature distribution. So you might have like a hot layer of, say, water and sitting on top of kind of a cold layer of water. So we'll talk about that. We'll talk about if you are simulating water heaters, what domestic hot water draws kind of look like. Then we'll talk about some control methods, some fairly simple rule-based control methods for water heaters that are run by electric resistance, and then for water heaters that are run by heat pumps. So probably the simplest type of thermal storage, I guess I would call lumped sensible thermal storage. So again, sensible refers to temperature change as opposed to phase change. And lumped means kind of one temperature throughout the entire tank. So you could think of this as a tank of, I don't know, it could be water, it could be sand, it could be some other, wax or paraffin, something like that. And actually, Zach shared an interesting YouTube video on residential sand thermal energy storage, which some people may have looked at, but that's down here on the website under the kind of read, listen, and watch portion. So how a sand battery could revolutionize home energy storage. The basic idea is that you've got some medium inside of the tank. You make it hot when, say, your efficiency of your heat pump is high, or when electricity prices are really cheap. And then later, when efficiency is low or electricity prices are high, you basically run maybe a working fluid through the storage medium to absorb some of that energy and then use it for heating later. Okay, so in this model, basically we use a thermal circuit representation to get the dynamics of this model, and it looks very similar actually in structure to the 1R 1C circuit that we used for space heating and cooling modeling. So here we have the thermal capacitance of the tank. So this is in units of energy per temperature. And typically we could calculate that by multiplying the density and the specific heat and the volume of the medium, whatever material is stored inside. And then we have a thermal resistance. So this represents basically heat transfer, or the impedance to heat transfer through the wall of the tank and potentially through the top and the bottom of the tank. Because it's a lumped model, we assume that there's one temperature everywhere within the tank, and we call that temperature T. So one number represents that spatially uniform temperature. And then TA here means, I guess, ambient. It's sort of the temperature that is around the tank. And then these terms here, the QC and the QD, have basically the same interpretation that they had when we were talking about heating and cooling buildings. So QC would be kind of the deliberate component of the heat injection. So if you're running, say, electric resistors to heat up the water inside of a water heater, this would just be the heat that's coming out of those resistance heating elements. And then QD here would represent sort of discharge thermal energy power, thermal power. So in a domestic water heater, this would be basically the water that we pull out for running faucets, showers, and things like that. Yes, question.
Okay, is that battery on the right of the TA, is that just supposed to represent like your energy coming in, your heat, thermal energy coming in?
Yeah, so the battery, I guess I don't strictly need to draw the battery in these circuits, but this basically, the role of this component in this thermal circuit is basically to maintain this temperature, the ambient temperature. So I guess you could think of this as like, if this is sitting in a basement and that basement is heated, I guess you could think of this as the action of the furnace or the heat pump or whatever it is that's keeping the basement warm.
Yeah, it's important to keep the basement warm because the basement gets cold, then it's going to absorb more heat from the thermal energy storage.
Yeah. That's one reason. Yeah, so if we think of like maybe a heat pump water heater sitting in a basement, why would it be important to keep the basement warm? Well, a heat pump water heater is going to basically absorb thermal energy from the air surrounding it and inject it into the tank of water.
So it'll have to do more work if okay.
Yeah, if the temperature gets colder and colder around
Yeah.
it, yes, it would have to work harder and harder. Its efficiency goes down. Also, potentially you don't want the basement to get super duper cold. If it gets too low, you might have to worry about pipes freezing and things like that. Yeah. Okay, but more generally, so if we're not thinking just about a domestic water heating situation, this could be a giant tank of molten salts that are used in a solar thermal energy power plant. So this is a plant basically that would concentrate sunlight using mirrors, make something super duper hot, and then use that heat source to run a power cycle and generate electricity. So this could be molten sand inside of a big industrial scale thermal storage device. Then QD would basically be the heat that you would pull out of that to run your power plant, your power cycle. And QC basically would be what we're getting from sunlight to heat up the storage medium. So these things can have different interpretations in different settings, but the basic model is more or less the same. Okay, so let's do a little bit of math and understand how that model works. So let's suppose, I guess, that there are kind of our safe limits, lower limit and an upper limit on whatever the temperature of the medium inside the tank is. So call those Tmin and Tmax here. And so the internal energy or the thermal energy stored inside of something is kind of similar to gravitational potential energy in that the datum that you choose, basically the point that you choose for zero energy, is arbitrary. That all the formulas that we have for that relate to things like internal energy or gravitational potential energy have to do with changes in the energy. And so when you do a delta of an energy, the base point, the place where you define it to be zero, ends up dropping out of those calculations. So we can pick this sort of datum, the 0 point, for the energy wherever we want. And let's leave it as a variable for now. And then we can define the stored energy, call it x, relative to that base point. So we call it 0 when the actual temperature of the tank is equal to that base or datum, anyway. So here's our definition. It looks very similar to the material that we went through for basically the thermal battery or the thermal energy storage representation of the heat capacity of a room or of a thermal mass inside of a building. So here we take the thermal capacitance C. This again would have units of energy per temperature, and then we multiply it by the temperature difference here. And then because the temperature is in this range, we get that the energy is in this range. So if we take the difference of kind of the CT max minus CT min, we would get the total energy storage capacity of the device. So far, so good. Okay. All right, and then you can do circuit modeling, or you can just do a first law kind of energy balance on the tank. We get that the rate of change of the internal energy here on the left-hand side is equal to the rate at which energy is leaving the tank. So this comes from basically passive heat losses through the tank wall. Those are a delta T over R sort of form. And then we add in whatever we're injecting, and then we subtract whatever we're extracting. And then we can plug in on the left-hand side here. T we can write in terms of X. So if we solve the definition of X, the energy for T, the temperature, we get basically this formula that shows up here. So then we can simplify terms here, and we get something that looks pretty similar to a battery equation. So on the left-hand side, we have the time derivative of the stored energy. On the right-hand side, we have minus X divided by RC. And here R times C, that product would have units of time. So you can interpret this as a self-dissipation time constant, similar to the battery parameter tau. And then we add in QC, and we have this floating term W, which is sort of everything that's not the X term or the QC term. And that ends up being all this floating stuff, the TA divided by R minus the TLS that shows up in the numerator. And then we subtract off the heat withdrawals, QD. Okay, so this is going to be a theme. Basically, all of the thermal storage models that we go through, we will end up with kind of a battery-like equation for them. and they will have slightly different definitions of the energy and of the disturbance W here, but they'll all end up basically in this. Yes.
What was TA? That's the ambient temperature.
Yeah.
Okay.
Yeah, that's the TA is the ambient temperature, the air temperature around the tank.
So then the term TA minus TLS is the difference in our outside temperature versus our reference temperature,
Yeah.
which is our reference temperature just like what? I know we're just kind of picking an arbitrary one, but what is it supposed to represent?
What does this reference temperature represent? So I'm leaving it as a variable because there are relationships between the different models, and we might eventually want to hook two models together. For example, a phase change model with a sensible model. You could imagine going through a process where you first melt something and then you raise its temperature.
Yeah.
And so in that case, you might want to choose these TLS, the benchmark temperatures, in a clever way so that your model is kind of seamless. So what would an obvious choice of this T here be? I probably would pick T minimum, kind of the coldest allowable temperature that we want. And in that case, your energy is defined as 0 when your stuff is as cold as you allow it to be. And does that make sense?
Sort of. So it's what you're trying to heat to. That's like the goal temperature, or not exact, I don't know.
Yeah, it doesn't have to be a goal temperature. It's really, you can choose it whatever you want. You could choose it to be absolute 0. You could choose it to be the temperature of the sun. You could choose it really anywhere in between.
It's just a big point for where you can model the change in battery power.
I would think of it as it's the point at which you define the energy to be 0. You say when the tank temperature is equal to this TLS, LS for lumped sensible, that's when the energy is equal to 0. So you think, what is a convenient 0 point for my energy? And then pick the corresponding temperature for that. Yep, no, good questions. Thank you. And again, just I don't want to belabor the point, but the analogy to gravitational potential energy, it's similar in that sense, right? Or the center of the Earth, or the center of the sun, or whatever it might be. Yeah, and you would get vastly different numbers for the gravitational potential energy depending on where you measure from. But usually when we talk about calculations involving gravitational energy, we only look at the changes, deltas. So yeah. Okay. So a couple of pictures of what lumped sensible thermal storage might look like. This is, I kind of love it. It's like a beautifully simple device. There are fancy names for it, but I call it a box of rocks. The idea here is that you have bricks inside of an insulated box here. So the white stuff here is thermal insulation. And then the U-shaped metal things here are electric resistance heating elements. So, and these are basically, they're not exactly the bricks that you would buy at Home Depot or whatever if you wanted to build a patio. They're slightly more cleverly designed than that to have pretty high thermal capacitance, so a good capability to store energy. But they're basically bricks. So when you want to store energy in here, you run current through these heating elements. You get I squared R joule heating losses from there, and they basically heat up the bricks. And then when you want to discharge the thermal energy storage here, there's a blower. This thing basically is a fan, would suck in air, blow it through the insulated chamber here, and then you would get hot air basically coming out the bottom of the device. So very simple. This is actually kind of cool because although you would lose energy through the wall, it's not perfectly insulated. You could imagine having one of these like inside your apartment. And so even though you're losing heat from this thing, you would be losing it in a useful way, right? So it'd still be heating up a room or something like that. Although these are not very common here, but if you travel to like Western Pennsylvania and you like, for whatever reason, if you go hang out at your friend's apartment or something like that, decent chance that they will have like, yeah, Pittsburgh sort of area, decent chance that they will have something like this. And the reason for that is when nuclear power was still being built in the United States at a significant level, utilities basically needed to increase electricity demand at night. They needed some kind of demand to like soak up the excess nuclear power because nukes don't really like to ramp up or ramp down very quickly. They just want to hum along steadily all day. And kind of normal electricity demand typically peaks during the daytime when people are active. So they basically gave these things away and said, run them at night, soak up all our excess power, and we'll run the grid more stably, I guess. If you go to Quebec, for whatever reason, if you visit Montreal or something like that, there's a lot of electric heating, and you'll find some of these storage systems as well. I think in UK, some places in the UK, they're common too. Yeah, so in why Quebec, right? Similar reason, I guess. There's a lot of hydroelectric generation in Niagara Falls and related stuff, and a lot of that power gets actually piped down to New York and the eastern U.S., but a lot of it also gets used locally. It's very similar to the what?
Coil, the coil in the battery 2000s. That we coil coconut inside the cooler, and they'll pour cold water to that so that it soak up the moisture from the air, and we just blow the thing and we'll get cold air.
I see. Yeah. So there's a similar sort of
Something.
air cooler that you could use. Yeah, like I guess if you had a lot of really cold water that you could get from a nearby lake or something like that, bring it home, blow air over it in order to cool a space. Yeah, totally. Yep. And actually, there are thermal storage systems like this, a little bit more mechanical than that, but we'll show some examples of that for cooling applications as well. So this, I guess, you'd call maybe like the point source storage, in the same way that a mini split we called like a point source mini split heat pump. We called a point source heating or cooling source, meaning it's done kind of at the zone level where people live, rather than done in a central plant and then having heat or cooling sort of piped around or blown around. But you can also get a box of rocks thermal storage in kind of a central configuration. This is a company called Steffs or Steffies. I'm not really sure how it's pronounced. But this again is a big insulated box of rocks. The white sort of blanket looking things here are thermal insulation. And here, this would be plugged into a duct system like you would have for a furnace or a central air conditioner. So you'd have cool air returning back from the house. It would potentially run over, these are the the heating coils of a heat pump. So you might run it over the heat pump coils to bring the temperature, say from, I don't know, maybe 66 up to, I guess in this schematic, 85 Fahrenheit. And then you would push that 85-degree air through these hot bricks, which might be at a couple hundred degrees Fahrenheit. And then you get an outlet temperature here that is, I guess, around 95 degrees Fahrenheit, a more comfortable kind of supply air temperature. So in this illustration, we have the heating from the heat pump working in parallel, I guess, or at the same time as the heating from the thermal storage system. You can really buy this thing. The shipping is quite expensive because the box of rocks weighs like about a ton. But I think this company Steffs is in North Dakota. So if you happen to have electric heating in that part of the country, it might be, I don't know, good option. Anyway, okay, so that's the lumped sensible, meaning, again, one temperature everywhere inside the tank. A slight different version of this, but a similar idea, is what's called stratified sensible thermal storage. And this ends up being sometimes a better model when the storage medium is a liquid rather than a solid, because due to natural thermal buoyancy effects, you'll tend to get a little bit of stratification inside of something like a water tank, where you get hot water up top and cool water in the bottom. Okay, so the schematic looks a little bit intimidating, but I'll walk through it here slowly. The basic idea is that we have a hot column of water up here, and then we have a cold column of water down here. The dashed line is what's called a thermocline. So cline like incline, thermo like temperature. So this is a steep temperature gradient, basically, where we go from hot to cold. And then because you have contact, basically, conduction between the cold water and the hot water, there could be heat transfer directly between the two layers. And that's represented via this heat transfer pathway with this thermal resistance. And then each of the layers potentially could be warmer than the ambient air here, which is a temperature TA. And so we'd have heat transfer through the wall from the hot layer and through the wall from the cold layer. And then as this thermocline moves up and down, really the state variable of this thing is what's called H therm. So, or if you like, it's the variable Y, which is just defined as 1 minus the ratio H therm divided by the total height here. So the vision, I guess, is that when this thing is fully charged, the thermocline would be all the way at the bottom of the tank. You'd have nothing but hot water. And then as you begin to pull hot water out, you'd replace it with cold water at the bottom. The thermocline would begin to move upward. and eventually would hit the top of the tank. And at that point, you say that you're out of stored energy. And then the capacitances and the resistance here, the R's and the C's, depend on really what the height of the thermocline is. So as the thermocline moves upward, the area here, the surface area for heat transfer is going to get smaller for the top layer. And so therefore the thermal resistance will get bigger and bigger until when y is equal to 0, meaning the thermocline is all the way at the top of the tank, this resistance actually goes to infinity, I guess. Do you have a question?
Yeah, so you mentioned that as you use hot water gets replaced at the bottom of the tank, right? Like at the bottom of the thermal gradient. So would you usually have like an inlet and separate outlet, like pump, like one at the bottom, one at the top?
Yeah, so the question is, for something like I guess a water heating application, I mentioned that we'd have an inlet at the bottom. Would we also have an outlet, say, at the top? And the answer is yes.
So is that similar to how a lot of like water heaters are? Like if I look at my, utility closet, like that's what my water heater should look like?
Yeah. So the question is that what water heaters look like? And the answer is yes. And I will show toward the end of this presentation, I'll show some schematics of what water heaters look like in practice. Mhm. Okay, so the assumption here is that the hot layer temperature and the cold layer temperature, the TH and the TC, that these are constant. And so the only thing that changes really is the height of the thermocline. So really we need just one equation that describes the evolution of the height of the thermocline in terms of what's happening thermally with all these heat transfer pathways. And if we can write down that one equation, then we fully characterize the state of the tank. So I think that there are some, in this derivation I'm going to put up here, I skipped some steps. And the first homework problem for next week basically is to like fill in those steps. So you'll know where you're going, but all the details of how exactly to get there, you have to figure out. Okay. Anyway, so we play a similar game here. Basically, we pick an arbitrary kind of datum, a 0 point temperature, and call it SS for stratified sensible. It may in general be different from the lumped sensible temperature. Right? And then we define the energy stored in the hot layer and in the cold layer relative to that kind of benchmark temperature. So they both of the energies have a thermal capacitance times the delta T. And the temperature that shows up for the hot layer is the hot temperature. For the cold layer, it's the cold temperature. And then they're scaled basically by this variable y, which essentially is a dimensionless, it's between 0 and 1. And when it's 1, the tank is fully charged. And when it's 0, the tank is completely empty. So let's just test that real quick. So suppose that y is equal to 1. That would mean that the XC, the energy stored in the cold layer, would be 0 because this thing here would be 1 minus 1.
So it's sort of like a quality calculation.
It's like a quality calculation from thermodynamics. Yeah, it's similar in that sense. Yeah. Okay, so here are our energies. We can then write down the total energy as just the sum of the individual energies. And you can do some algebra and show that it has this form. So the C factors out, and we have basically some temperature terms here multiplied by y. And depending on the value of y, we understand what basically the bounds are. So we have a C delta T for the lower and for the higher limits, basically, of the stored energy. And then if you took the difference here, that would tell you, so if you took C times TH minus T benchmark here, and you subtract off the lower limit, we would get just a C delta T term. And that would just be C T hot minus T cold. So here you can see that the benchmark temperature T SS here would drop out of that calculation. Okay, and then we can also do kind of a conservation of energy balance here. So the rate of change of the internal energy of the tank, we can write down, and you can convince yourself that this is the right formula there, basically by looking back at the schematic. And then again, you do some algebra basically, and then show that this thing has essentially a thermal battery form. So the same form that we had, in fact, the exact same equation that we had for the lumped sensible model, but the definition of this W here is now slightly different. So it still has the ambient temperature and the thermal resistance in it, but it has, in general, a different benchmark temperature, and it has the same QD. And then this R and C actually would be the same as the R and C that show up in the other model. And so the time constant, tau, in the denominator here would be the same for both models. So again, I guess homework problem number 1 is basically to fill in these dots for next week. Okay, so here is a schematic. This is from, I guess, the Bonneville Power Administration, which is a public power administration that operates in the Pacific Northwest of the US, which is another one of these regions where there's a ton of hydropower. So again, I guess thermal storage pairs well with hydropower, at least it does in Quebec and in the Northwest. So anyway, here's the idea. Blue means cold, red means hot. And there's kind of a fairly narrow layer. We call this the thermocline, where we have a steep temperature gradient. So here we're plotting, it's a little weird, I guess, but we're plotting the volume of the tank on the y-axis, and we're plotting the tank temperature on the x-axis. So as you go up along the y-axis, you are moving basically up along the tank volume. And so you can see the temperature goes through this very steep thermocline, and then it's basically constant within the hot layer. So this is a pretty good model of how something like a hot water storage tank would work. And this would be the inlet of cold water, and this would be the outlet of hot water. So you can see that the tank is really designed in order to maintain this thermal stratification, so that you basically are delivering hot water until the thermocline gets all the way up to the outlet. So that's two kinds, or rather, I guess, two subsets of one kind, the sensible thermal storage. So let's talk about latent thermal storage, which is about phase changes rather than temperature changes. Yes.
Do different liquids have different like temperature gradients? Like that middle section of that graph could be, longer and at a, a higher slope, I guess. And, if you had like a more thermally, radiative liquid, does that matter?
Yeah, so the question, I guess, is would different substances, different liquids, show different kind of temperature graphs here, temperature dependence, different steepness of the thermocline and things like that? I actually don't know. I haven't really thought about that. I could speculate and say it's something about the thermal conductivity of the fluid and probably something about the viscosity of the fluid. So, how does the thermocline, the stratification get degraded? How does it get mixed? So one would just be sort of thermal buoyancy effects from water circulation. So I guess if you had a super viscous fluid, something like oil rather than water, there would be not as much of that mixing effect. And then I guess the other way is you can just have direct, basically, conduction. You have a cold layer and a hot layer, and they're touching each other. So you'd have heat flowing from the hot down to the cold. And so if the thermal conductivity of the substance is high, then I guess you would have more heat transfer and therefore more kind of degradation of the stratification. Yeah.
And then why is it called sensible thermal storage? That just seems like a funny modifier to me.
Yeah, so sensible, again, I don't know why exactly we use this term, but sensible refers to temperature change thermal storage. So I guess it probably goes back to like sensation, right? You can feel it when you're storing energy in something by changing its temperature because it gets hotter. Yeah. Whereas if all you're doing is sort of melting or freezing something, the temperature remains constant, so it feels the same, but it would just be more liquid or more solid. Zach, did you have a comment?
I guess when you said the more conductive the thermocline would be farther out or have a larger region, more faster.
Well, okay, so I guess I'm not sure about the steepness of the thermocline. I guess the point I was trying to make was if you had a really conductive fluid, I'm actually not sure an example of that, but I guess like a liquid metal or something, like maybe mercury is really conductive. Then you would just have faster heat transfer between the hot layer and the cold layer via conduction. So I think over time you would tend to degrade the stratification here. I actually don't know if that would translate to a steeper thermocline or not. Anybody want to hazard a guess?
Thermocline's a good word.
It's a good word, thermocline. Yeah, it's fun to say. Yeah. Anyway, okay, so let's move on to latent thermal storage or phase change thermal storage. By the way, if you're like a graduate student and you're doing thesis type research, on anything related to thermal storage and you start doing a literature review, you will find an enormous body of work by material scientists and mechanical engineers and others that basically play around with different materials and evaluate how good they would be as thermal storage media. So how energy dense are they? How conductive are they? All these sorts of things. And people get into this whole science of kind of manufacturing carefully fabricated materials for that purpose. Question?
Previous one, what's the application of, where these kind of thermal storage systems used, like cold and hot?
Where are these stratified thermal energy storage systems used? The most popular one, I think, is domestic water heating or residential water heating. So if you go into the basement of your apartment building, you'll probably see a big cylinder tank. And it probably, if you touch the bottom and touch the top, probably it would feel cooler on the bottom, hotter on top. Be careful, don't touch a boiler or anything like that. But this basically is a reasonable model for domestic water heating. It's also used in much bigger kind of industrial applications. So there was a big proposal here. It didn't actually get built, but there was a proposal on Purdue's campus to build a really large chilled water storage tank that would, I don't remember the volume of it, but it would store a huge amount of cold water. And the idea there is that overnight, it's more efficient when it's cooler outside to make chilled water. Also, we have lower electricity prices here overnight. So the idea would be during summer cooling season that you would make a whole bunch of cold water during the day, or sorry, during the night. And then during the afternoon, when demand for electricity peaks and also electricity prices are high, you would use that cold water instead of running the chillers to provide air conditioning to campus.
But why not rather a separate one for the cold one and separate one for the hot one? Is it just to reduce the space that it's take on the, like it has something to do with the efficiency?
Yeah, why not do a hot tank and a cold tank? Yeah, I guess something about space efficiency, maybe. It's easier to put in one big tank than two small tanks, I guess.
But the goal of this tank is just for hot water, right? And the idea is that as you pump hot water out, you replace it with cold water, and then you would just heat that cold water. Right? So
Yes.
it should all be in the same tank. The point of this tank isn't, if I'm understanding correctly, to get cold water out, it's to get hot water out.
Yeah. The point of this one, as illustrated here, is to get hot water out. So right, we would pull hot water here, and then return cold water here in something like a closed loop system.
Yeah.
And I guess for cold water storage, it would be similar, but just kind of reversed.
Yeah.
So you would pull cold water out here, run it around campus for air conditioning, and then you would get the return water coming back at a higher temperature, and you would dump that basically in the top of the tank. There are other applications of thermal storage, industrial applications. There's something called a Carnot battery, kind of a new and interesting concept, where basically you would have two thermal storage. Wait, am I getting this right? You'd have a thermal storage system that you would, when electricity is cheap, you would run a heat pump to basically warm up that, heat up a bunch of water, something like that in thermal storage.
Yeah.
And then when electricity is expensive, you basically run a power cycle, a steam cycle or something like that to generate electricity. And the heat source for that power cycle is the stored, the thermal storage device. So I'm not sure if it's economically viable, but a lot of people are trying to figure it out and building prototypes and things like that. Okay. All right. So now I feel like I've gone to this slide like 4 times.
Yeah.
Okay, so now we really are going to do latent thermal storage. So this is about freezing and melting, or I guess it could be about boiling and condensing, but usually it's transitions between the solid and the liquid phase that people use here. So the model will involve what's called a latent heat of fusion, which is the amount of energy needed basically to melt a kilogram of substance. And we will also pay attention to the melting point of the substance and call that Tm. So already you can see, depending on the application, a heating application or a cooling application, low temperature heating versus high temperature heating might determine what material you want to use for your storage medium, because it would determine basically this melting and freezing point. Okay, so the state variable here we'll call ML, which is the mass of liquid stored in the tank. And M here is just a parameter, would be the total mass of your thermal storage material. So the mass of solid in the tank would just be big M minus the mass of liquid. And then again, we define the energy relative to some arbitrary, call it a 0 point temperature or a datum of temperature. So we define that as C times the melting point minus TL. And this is a little bit of a weird definition, and I will explain, I guess, in a little bit why we choose this particular definition. But you can think of this as, TL being below the melting point. So this would be the energy required to raise the temperature of the storage material up to the melting point. So it's solid, and you have to add energy to raise its temperature until the melting point. And then the additional amount of energy stored would be L, the latent heat of fusion, times ML, the mass of melted liquid. Anyway, and then you can write down basically the upper and lower limits for this definition of the stored energy. And if you take the delta here again, you would get the energy capacity, and that would end up just being L times M. All the C terms here would drop out. Okay, so again, we can do a conservation of energy, a first law balance on the tank. We get the rate of change of the internal energy is equal to basically what we put in, plus this disturbance W. And we get a disturbance definition that looks very similar to what we had for the other models. So here's an example of what latent thermal storage looks like. Probably the most common phase change thermal storage medium is just water. So here, for scale, you can see the person here is probably about 6 feet tall. So this is a very large, basically, it's either a swimming pool over here or it's an ice skating rink over here, depending on if the water is frozen or not. And so all of these plates here, I think, it's a little hard to see, but I think that they are plates of a heat exchanger. So these would have, they'd be very cold, basically, because they're in contact with a refrigerant that's below the freezing point of water that's circulating through these. So when you want to store cooling, I guess you would run very cold refrigerant through these. It would freeze. And the reason that the water level is higher here than it is over here is that water expands when it freezes, right? And then later, if you want to recover that stored cooling that you made, say, overnight on a hot summer day, you want to recover it during the afternoon, you would basically run water over the ice. It would melt some of the ice, and then you would get cold water to supply for cooling or whatever. So here is a schematic of what that might look like that has all the mechanical equipment in it. So this is the big either swimming pool or ice rink, depending on its phase. And then this is an illustration basically of the heat exchanger coil that goes through the medium. You might have something like glycol that you can make very cold, but still pump around as the sort of coolant that goes into the water here. So this would be a cooling tower. This is where we exhaust basically ultimately the heat that we pull out of the water. This is essentially a refrigeration cycle here that runs between the condenser water, which circulates through the cooling tower, and this glycol loop here. So there'd be a refrigerant that's circulating kind of inside of this chiller, and that's making the glycol very cold. Glycol pumps through here, freezes the ice. And then this is the discharge side to actually pull that, extract that stored kind of cool energy and use it to provide air conditioning to a building. So here we're extracting chilled water, I guess, pumping that through a heat exchanger, and then there's probably a closed loop of chilled water that circulates through this air handling unit here. This would be pulling back warm return air from the building, mixing in some outside air, and then blowing that fresh mixed air to the building. I actually don't know what purpose this air pump serves. Something. Yep.
I know, I think in 2022, Purdue got into the news about a professor recently figured out supercharging cables. They used a latent water to gaseous mixture to the cable so it could do faster charging.
Oh, interesting. Okay.
Yeah, the heat generated from the wires is one limitation to how fast you can charge a vehicle.
Okay, so to do super high speed, I'm just trying to paraphrase for folks online. To do super high speed electric vehicle charging, you want basically super low resistance, electrical resistance in the wiring. So you want superconducting wiring, is that right?
No, not super, it was mostly just like, I think they were passing like 200 or 400 amps. They like doubled the amount of amperage you could pass through just a typical like Tesla charging cable outside in the weather by adding latent heat to the like casing of the cable.
Oh, I see. Okay, so they
It's
made
not-
casing of a cable that would basically, the casing had a phase change material in it that would melt when the wires began to get hot, and that would provide additional cooling to the wires to allow more current to flow through them to do super fast charging. Cool. Interesting. Yes.
Would that ever, if the coolant or whatever, was the insulating liquid got hot enough, then would that slow it down even more? Just, because it would stop, then what would be cooler air from getting to the wire?
Potentially. So the question is, what if you got through melting all of that phase change material? Now you have more material wrapped around the wire that you're trying to dissipate heat from. Would that provide essentially additional thermal resistance? I guess, yeah, right. So you'd want to,
Have to be only for short charge.
yeah, and you'd have to,
Supercharge.
yeah, and then maybe you cool it back down in between charges or something like that. Yeah. Mhm. Yes.
Could the air pump be to like keep the water circulating so it doesn't freeze on your heat exchanger basically, and you end up with impossible leaking?
Yeah, that might be there to help with melting if you're trying, because like, I don't know, can't you, like, why do you have to have such a deep pool of water instead of just like kind of a sheet, like, can the ice be more thin than like, I feel like if it is super thick, it's then difficult to, I don't know. They probably know more than I do.
I'm not really sure why thick or thin, why deep or shallow pool here.
Just
I guess, yeah, probably more energy per square foot of, valuable floor area. Someone suggested that the pump might be basically to kind of keep the water moving a little bit so that it doesn't freeze up so much on the coils. That could be.
Yeah.
Yeah, so how do slushy machines keep the slushy from freezing, becoming a popsicle? Oh, I see. The thing is just always spinning,
Yeah,
right?
Freeze
Yeah,
the block.
Yeah.
The block is always.
it's always spinning.
Just
Yeah.
little crystals.
Cool.
Man, or slushy.
Yeah, oh, should I go out for slushies after this? Yeah, it might be. It's like,
Freeze outside.
great. Yeah, we could just pick up some snow and add some food coloring.
Exactly.
Okay, so to summarize, all three of the storage types that we reviewed follow basically a heat battery model. They all have essentially the same equation that we have for an actual electrochemical battery. They have energy capacities, and they have this kind of first order linear dynamics that feature a self-dissipation time constant, and then kind of a term that we control and a term that we don't control. So discrete time dynamics of this, and actually I will, for the first time, I will not make you do a homework problem on this where you have to derive the dynamics. I trust at this point that you've done it enough times that you know it. But you could, if you want to go through it, you can show again that these are the dynamics. And for two of the three models, the latent sensible and the lumped sensible and the stratified sensible, for those models, we have finite time constants. This thing tau that we divide by is a number, not infinity. But for the latent model, actually, there is no minus x on RC term that shows up in here because the heat transfer through the boundary of the storage system is not really dependent on how much of our material is melted versus solid. So for that reason, there's basically no x over tau term up here. And then we don't get the A term here. We just have a very simple formula involving the time step. And then there are different definitions, and you can go back through the slides and catalog them if you want to, but I did that for you here of what the state is, the max and the min energy storage levels, the self-dissipation time constant, and then this disturbance term W that shows up, the additive term that shows up over here. I'm going super slow, so I'm going to try to speed up a little bit. I think I might just skip this, but the big idea is that because we have a lot of flexibility in these models, and in particular, it's flexible, our choice of the sort of 0-point temperature, the datum of temperature, we can make clever choices of these things so that one model, this kind of first order linear model, can actually represent smooth switches between different storage kind of physics. So we could go, for example, from a lumped sensible model to a stratified sensible model or we could go from a phase change model to a temperature change model. And there's an example here. I guess in the interest of time, I'll just skip it, but you can follow through if you want to see how that would work. Okay, so how do we charge or discharge thermal energy storage, and what are the efficiencies or the coefficients of performance related to that? Well, discharging typically doesn't take very much energy. It's typically just running a pump to circulate a working fluid, sometimes a fan to blow air over some hot bricks or something like that. And for charging, typically we would use either a refrigeration cycle or a heat pump cycle. Or if we want really high temperatures, maybe too high to realistically get with a heat pump cycle, we might use electric resistance. Okay, and so we already basically have gone through how to find COPs for things like that. All right, so let's talk about some typical values, how you would calculate them. For the thermal capacitance, fairly easy. You just look at the density, the specific heat, and the volume of the stored medium, and multiply them and you get C. And then for R, the thermal resistance, it's the reciprocal of the product, U, the thermal transmittance, times A, the surface area of the tank. And U typically is very low because you can wrap a thermal storage tank most of the time in some insulating material. So it's kind of in this 0.001 kW per degree per unit area. And then, yeah, this basically, I'm just giving you examples here, the numerical values for water, which is very often the storage medium that we use in thermal storage applications. So we've got the density, specific heat, the product here that shows up, and then the latent heat of fusion as well. And then the area calculation, the area is relevant up here for R, and the volume is relevant up here for C. And if you have a cylindrical tank shape, we've got formulas for the volume and the area, and we can express those in terms of basically two parameters, the radius of the tank and then the height of the tank. So let's look at the example of a domestic water heater and maybe ask how much thermal energy we could store inside of a water heater. So let's assume the stratified model, hot layer sitting on top of a cold layer with a thermocline in between. So here the energy storage capacity is, I guess it's always defined as the max energy minus the min energy. So that ends up just being C times the temperature difference between the hot and the cold layers. So our capacity for storing energy really is a function of how hot or cold we can make the two layers in our stratified tank. We've got typical values for the volume, might be kind of on the order of 1/3 of a cubic meter for, I think that's like somewhere between 50 and 80 gallons is this 0.2 to 0.3 range. And if we plug those in, we get numbers of C that are around kind of 1/3 of a kilowatt hour per degree Celsius. The cold temperature here would really be a function of how hot or cold the water is that comes out of the municipal water pipes. So this would be quite low in winter, right? When washing your hands with cold water, it feels super duper cold. And it would be much higher in summer when you get fairly kind of lukewarm water coming out of the tap. But call it about 15 degrees, just as a round number. And then we need to know T hot, the number basically that we store our hot water at. And there's kind of a plausible range for this. So if you get too hot and somebody runs the hot tap, a kid or whatever turns on the hot tap, it'll burn them. So typically you're not allowed to store at super high temperatures. About 60 Celsius is kind of the limit. And then below about 50 Celsius, there's a type of bacteria called Legionella, which can grow in domestic water heaters. And so you don't want that happening either. So you've got kind of a 50 to 60 C range. So pick, I don't know, or kind of random number 51C and compare, basically plug in T hot, T cold, and the thermal capacitance, and you get kind of order 10 kilowatt hours of thermal energy stored in a typical water. So that's comparable to the amount of energy that would be stored, for example, in a Tesla Powerwall, one of the common forms of electrochemical battery storage. But remember, we're storing thermal energy in a water heater versus electrical energy in a battery. And so there's kind of a difference in sort of quality of stored energy there. Okay. Yes, question.
Dissipation rate as well, like in thermal energy storage, the dissipation should be more than like electrical energy when considering batteries and stuff like that.
Yeah, so the question is, could we explain kind of the self-dissipation mechanic? So for or the physics of self-dissipation. So for thermal energy storage versus something like a battery, how do those two compare? Yeah, so I think ran through calculations of the time constant for a battery, and we found it's kind of typically on the order of about 1,000 hours. If you look at, let's see, a water heater tank, I think we ran the numbers here. Did we? No, we have C, but not R. R is usually quite large. C might be about a third. So for a water heater tank, you might actually have similar, like about 1,000-hour time constant, somewhere like that. So yeah, that tells you that the self-dissipation rate of a water heater might be similar to that of a battery. And part of that is because you can really insulate the heck out of a water heater tank. So when we were talking about thermal energy storage, kind of passive thermal energy storage in building air and thermal mass and stuff like that, we talked about time constants being on the order of maybe 1 or 10 hours, somewhere in that range. So you get much faster self-dissipation of the sort of virtual batteries that represent the air and the thermal mass. Does that make sense? Oh, yep. No, it's great, thanks.
I saw that like for like the bacteria is one for this for like how composting gives off a lot of heat. Are there any applications for doing that?
Yeah, so the question is, it was triggered by this sort of bacteria thing. And the question is basically some bacteria, when they like eat or whatever, they go through their normal biological processes, they generate a little bit of heat. Are there technologies that basically harvest that heat and use it for something? I don't know. I know there's something called an anaerobic digester that are, they're used on farms where you put in waste from the farm and you get out, typically not heat, but you'd get out something like methane from the decay due to bacteria eating compost and stuff like that. I don't actually know about the waste heat question. That's an interesting. I would love it if you would Google it and tell me what you find out. Yeah, thanks. Okay, so the homework involves simulating domestic water heater and its behavior. So I want to run through really quick how we might basically get an estimate of energy that people use for water heating in homes. So the main use of domestic hot water in residential settings is baths and showers. Of course, there's also dishwashing and hand washing and stuff like that, but it ends up being much less. And if you look at data from real homes, you typically have about 16 times N, where N is the number of occupants in the house, and 16 is roughly the number of gallons drawn in one shower or bath. So we have about 16N plus 4, and here the 4 represents kind of the hand washing and toothbrushing and whatever else is that we do with hot water. Do you guys brush your teeth with hot water? Usually cold for me as well. Yeah, but who knows? Anyway, so yeah, this tells you an idea. Basically, if you look at roughly 16 gallons and a typical shower lasts maybe 8 to 12 minutes, somewhere in that range, this tells you roughly the volumetric flow rate of water being about 2 gallons a minute, something like that for a shower. Or in cubic meters, we get about this number. Just as a benchmark, right? If you're running a simulation and you want kind of a sanity check. And then to calculate the thermal power associated with water draws, well, if we have the VDOT, call it 2 gallons per minute of the volumetric flow rate, the thermal power associated with that is basically the density times the specific heat times the VDOT. So this thing here would be basically an M dot times C. And then we have a delta T here. So this again comes from the incompressible substance model applied to water here. And T, this is the, I guess, the supply temperature, the tank storage temperature, and then Tn would be the inlet water temperature coming from the city pipes. And here is a graph of a model, I guess, pulled from this, what's called Building America database. But basically, this is over the course of a year, this is what that inlet water temperature looks like. So it's lowest about now in mid-February, and it's highest kind of in the warmest part of the year, mid-August or so. And it varies, the average is about 15, and it varies between kind of 9 and 21, somewhere in that range. So this, of course, would be a little bit different depending on where you live and so on. If you lived in Florida, this whole curve would be shifted upward. But this is a fairly representative temperature profile for the US. Okay, so if you plug all these numbers in, we've got the thermal power formula up here. We gave values for all these constants. So you might find that the thermal power draw associated with kind of running a shower might be about 20 kilowatts, which is a lot. So electric power consumption of a house might be, on average, typically in the 3 to 5 kilowatt range. So when you're running a shower, you're consuming energy at a fairly fast rate. Yes.
I guess this is assuming that all 2 gallons is only hot water.
Right. Yeah, so the comment is that this is assuming that the full volumetric flow rate, the full VDOT here is for hot water and not for mixed water. Whereas most people, yeah, would mix in some cold water with the hot water. Yeah. Yeah. Okay, so that's a nice segue into kind of this distinction between the hot water and the mixed water. So I don't know if this is widely understood or not, but it took me a little while to wrap my head around it. But the idea is that the withdrawals that we do for things like showers and baths typically are not a function of the tank temperature. And that's not obvious, but I'll show what I mean by that. So most of us, we have kind of a water temperature set point. Typically, pipes basically have a constant mixed water flow rate, MDOT. So if we mix in more hot water, we put in less cold water, basically. So this is roughly constant. And typically, we have an idea in our mind of like how hot or cold of a shower we want. Yeah, exactly. You know exactly where it is, the quarter turn or whatever it might be. You might not know exactly what the number is, but you have an idea in your head somewhere. So the idea is that you can fiddle with the dial until you get the temperature that's comfortable for you. So this is the mixed water temperature. So we have MDOT, the flow rate of hot water, times T, the hot water temperature, plus whatever is left over, MDOT star. This is the overall mixed water flow rate minus the hot water flow rate, times Tn. So this is basically a weighted average, weighted by the flow rates. And we want that to be, just right for us. This is just the temperature that you want for bathing. Okay, so we can do some algebra, multiply through by MDOT star, and then group terms by MDOT. So move this MDOT Tn over here. And then what do? We move over the MDOT star term to the right-hand side. So we have only MDOT stuff on the left. We have only MDOT star stuff on the right. And this term on the left is basically the heat transfer associated with the mass transfer of this hot water being replaced by cold water. So this is the heat that we're pulling out of the tank. And then everything here on the right-hand side is independent of the storage temperature here. So the idea basically is that if we store the water in the tank at a hotter temperature, people will just mix in more cold water. And so we get roughly the same energy withdrawal either way. Does that make sense? All right, so this gives us basically a way to simulate water draws. So, N, the number of occupants in a house, you might imagine you have roughly 1 shower per person per day. And we have kind of an energy or power rating of what the draw is. And we know roughly the duration associated with baths and showers. So you could imagine writing some code that would randomly generate power draws and associated with showers and place them at kind of plausible times. Some people shower in the morning, some people shower in the evening, so you do a couple showers in each frame. And I think this is the approach that I use. I don't think I asked you to do it in the coding problem for this week, but I implement that. So that's an idea of where that code would come from. I promised that we would show a schematic of kind of the water heater that lives in your basement or your utility closet. Here is what a typical one looks like. So they're designed to maintain thermal stratification. And the reason for that is even if your tank is mostly depleted, you want to still be able to pull out hot water rather than pulling out kind of lukewarm mixed water. So we have the hot water withdrawal typically is at the very top of the tank, and the inlet, the cold water inlet would be near the bottom of the tank. Oh, sorry, maybe not. It looks like it comes in from the top, right, through this long tube, and then it would get actually injected into the water near the bottom.
You can have them either way.
Oh, sorry, was there a comment online?
There's water heaters that you can either have a bottom outlet or a top outlet on them.
They can either have
so typically on the top, you can kind of see that dip tube that goes down and forces the water down. So that's how you still get that stratification.
Nice, gotcha. Yeah, so some of them may be designed with the cold water inlet down here, and some may be designed with the inlet at the top and this long tube to basically force the water to the bottom. Yeah, thank you. Okay, and then electric resistance water heaters typically will have two heating elements, one near the bottom and one near the top. And they'll usually both be rated at about 4.5 kilowatts, although that varies a bit from manufacturer to manufacturer. And usually only one of them will run at a time. So here is roughly the control logic that a lot of resistance water heaters will use. So the basic idea is to run the bottom resistor, to associate with each resistor a temperature measurement. So you might put a thermocouple on the outside of the tank underneath the insulation that's at the same height, basically, as each of the resistors. And if the bottom resistor, the bottom temperature sensor measures cold, basically, then that means that water is being used. And so you turn on the bottom heating element and try to warm up that cold inlet water. And then if the thermocline moves up to the point where now you have cold water at the very top of the tank, then you switch. Basically turn off the bottom resistor and turn on the top resistor. And the reason for that is you want to deliver as hot of water as you can during those kind of cold shower or lukewarm shower moments. And then you continue running the top thermistor until the thermocline basically moves back down below the bottom heating element. And then typically switch to the bottom or else just turn off the thing. So here's an illustration of that control logic. So we start off, say, with a fully charged tank. And then someone starts taking a shower. We begin getting cold water at the bottom of the tank. So here, orange means hot water, blue means cold water. And for the resistors, red means on and blue means off. So as soon as we start measuring cold down here, we would turn on the bottom heating element. Say a shower continues. So even though we're heating as much as we can't keep up with the roughly 20 kilowatts of thermal energy withdrawal compared to our, say, 5 kilowatts of thermal energy injection. So the thermocline keeps moving upwards. And eventually we get cold water measurement up here, and then we turn on the top heating element. Okay, shower stops, and then we begin to warm the water back up. The thermocline passes this resistor, so we turn off the top element and turn on the bottom element. And that continues to pull the thermocline downward until it's below the bottom heating element. And at that point, we would turn off the resistor. And we're back to kind of the initial state. Make sense? Yes. Why can't we have both on at the same time? There's no real reason other than the wiring that goes to a water heater. Typically, it might be only rated for, say, 15 amps or something like that. So if you have a limited amount of current that you can flow, you kind of want to put it where it's most useful, basically. But yeah, you could imagine a design that had, two 2-kilowatt things rather than one 4-kilowatt thing on at a time or something like that.
So you can't, when you get into commercial water heaters, you can actually have simultaneous and non-simultaneous on the heating elements.
Oh, that's really interesting. I
Just
didn't know
because,
that. So
yeah,
for the folks in the room, the comment from online is basically when you're dealing with commercial water heaters, you can have systems where you have simultaneous running of the top and the bottom heating elements. Cool. Thank you. Okay. Yeah, okay. So this, I think, is getting into your coding problem for next week's homework. So you will need to implement some logic like this. The basic idea for simulating this resistance-only water heater controls is that, at least in the residential setting, and again, thank you for adding that background about commercial water heaters. But at least for smaller residential units, typically we only run one resistor at a time. So the model here, and this is not a perfect model, but it's a reasonable emulation of the actual logic, would be to basically try to come up with, we're trying to come up with this QC here, the amount of heat that we inject into the water. So we try to find the value of QC that places basically the next energy exactly at the maximum amount of stored energy. So we're going to heat as hard as we possibly can, but we will cap the amount of heat that we're allowed to inject at the capacity of the electric resistor. So this would again be maybe 4.5 kW. So these are basically the things that you will code in your homework, I believe. Anyway, so these are equations that basically do that. They do that logic, but in a kind of clean and mathematical way. And here we set the electric power equal to the thermal power that we deliver, because for a resistance water heater, the efficiency is basically 1. So we're getting close to time here, but I want to talk as well about heat pump water heaters, and then what are called hybrid heat pump water heaters, which have both a vapor compression cycle and electric resistance. And they use them kind of in tandem in a primary and then a backup fashion. But here's a schematic of what a heat pump water heater would look like. So here we have the cold water inlet at the top of the tank and the hot water inlet again at the top of the tank. The coil that wraps around the tank here is the condenser. So this is basically a heat exchanger where hot refrigerant is flowing through, and it's condensing and cooling basically as it warms up the water that it's in contact with. And then typically we would have 1 or 2 backup electric resistance heating elements, so that when there's not enough heating capacity coming from the vapor compression cycle, we can run the electric resistance to augment it. And then the function of the vapor compression cycle, the heat pump cycle, would be to suck energy out of the ambient air. So we have warm air coming in here. There would be a fan that's moving air over the coil. The evaporator coil is up here in this top unit. It would absorb energy, basically run really cold refrigerant through this hot airstream, or warmish airstream, and it would absorb energy, which then is moved into the water via the condenser coil. And so that would cool down the air, and this is why we get kind of a cooling and potentially a dehumidification effect in the room that surrounds the water heater. Okay, so for a heat pump only water heater, the logic is fairly similar. The basic idea is that anytime the tank is not fully charged, so there'd be a temperature sensor near the bottom of the tank, and you would just say, look, anytime you measure cold, that means water is being used, and we want to basically run the heat pump in order to try to refill the tank. So again, we try to place the next water temperature, xk plus 1, at the maximum, or the next stored energy, rather, at the maximum value. But again, we clip our the actual thermal power that we deliver, we clip that within the limits of our equipment. So here, rather than just having P max, we would have our efficiency, our COP, times P max. And the COP in general could vary over time, depending on both the water temperature in the tank that it sees, but also depending on the ambient temperature in the room. And so here are equations that basically implement that logic in a kind of clean fashion. And then just like we talked about how sometimes people for space heating applications will install an air source heat pump as well as electric resistance, kind of backup heat. Hybrid heat pump water heaters, which are, I think, the most common type of heat pump water heater today, do the same thing. So the logic here basically is that, again, anytime the tank is not full, we want to run the heat pump because it's the most efficient thing. But if the charge here, which you could think of the height of the thermocline, I guess, if the charge drops below a certain threshold, a minimum acceptable value, then we turn on the backup heat. And that could be turned on in addition to or separately from the heat pump. And I think different manufacturers do this in different ways. Some have a big heating element and they will turn off the compressor for the vapor compression cycle and turn on the big heating element as a backup. Others will run the vapor compression cycle and then a smaller heat pump, a smaller heating element as a supplement. Anyway, here is, again, not perfect, but kind of reasonable logic that you can implement that roughly emulates that behavior. So as always, we try to place the next temperature at the max, but we saturate. So if we're above the kind of minimum, the sort of danger level, then we just use the heat pump. And so our logic and our formulas are the same as they would be for the heat pump only case. But if we are below that kind of critical level, then we go into backup mode and we turn on the heat pump as well. So the saturation here of the thermal power would basically be at whatever the compressor can deliver plus whatever the resistor can deliver. And here are formulas that basically deliver that. The P formula looks a little bit weird. I think I have an illustration here. It comes from this schematic, basically. So here I showed one of these, the same plot, I think, when we were talking about space heating. But the idea is we have the thermal power that we're delivering to the water on the x-axis. On the y-axis, we have the electric power that our heating plant is consuming. So if we're not delivering that much thermal power, we're kind of within the capacity of the heat pump. We have a slope 1 over eta here. So electric power is increasing fairly gradually with the thermal power. But then we have this kind of kink and we begin to use electric power much more quickly with a slope of 1 here. And this is the resistance turning on. Okay, so here's an example of what this looks like. I'm simulating here a hybrid heat pump water heater. So electric resistance plus a vapor compression cycle. On the top plot here, we have the thermal power that we are pulling for baths and showers. The middle plot here is the stored energy in the tank. And the dashed line here, horizontal dashed line, is kind of the minimum acceptable energy. So you can see the tank begins fully charged. We start pulling water and the temperature or the stored energy in the tank begins to drop. And then as soon as we begin to drop at all, we turn on the heat pump, which is the low power here, about, I think, half a kilowatt of power consumption. And then when we get below this kind of danger threshold, water's getting very cold threshold, then we turn on the backup heat as well. And so we get, I think, about 5 kW, 4.5 from the heating element plus half from the compressor. Yes.
I see you modeled the like I'm assuming that's like a shower up on the top.
Yeah.
As like a big increase. And then what is that like little bottom step? You know, like halfway, it seems like your power goes down. What's that supposed to be?
Yeah. So the question is like, what's happening up here with the water draws? And the answer is this is 2 back-to-back showers.
Well, that I understand.
Okay.
Like the showers, it seems like they start at like a high.
Oh,
power,
yeah.
They step down.
Right. Okay. So if we look at this one, why is it high for a while and then
Yes,
low
yeah.
for a little while? Yeah. So the answer is it stems from basically how I am simulating the water draws.
Okay.
So I think what I did is I specified a power, call it 20 kW, and a duration, call it 10 minutes.
Okay.
You multiply those two together, you get an energy.
I see. So it's
And
just,
then-
like that, the area under the curve there is 20 kilowatts and it's just over some amount of time.
Exactly. The area under the curve is whatever that comes out to be,
Okay.
4 kilowatt hours or something like that.
Okay.
And I basically, yeah. So this model is basically like at the start of a time step, I begin my shower and so I'm drawing power full blast until the last time step. There are multiple time steps that are being sort of spanned by the shower.
Little cold
And
start
then,
at
yeah, at the
Wake you
end,
up, yeah.
exactly, a little cold at the end there, I guess. Yeah. Anyway, so I think this is what the outputs of your code should look like for the homework problem. So I guess I ran out of time. I wanted to show you a little bit of MATLAB code, but maybe we can do that. Well, I guess Tuesday would be a little bit too late, but you can do that in office hours next week. All right. So thanks all for your time. Have a good weekend, and I'll see you on Tuesday. Oh yes, question. See the YouTube video for that. Yeah.